Hello, my name is Daniel Nenny, and I'm the founder of SemiWiki.com, the open forum for semiconductor professionals. Since going online in 2011, SemiWiki.com has experienced more than 4 million users. If you're not a member of the SemiWiki community, please register as my guest. I hope to see you there. Today's webinar is titled Architecture Exploration of System on Chip using VisualSim, Hybrid RiskFi, and ARM processor libraries. The speaker today is Deepak Shankar, the founder of Mergeless Design, and has been involved in the architecture exploration of over 250 SoCs and processors. Mr. Shankar started Mergeless Design because of a vacuum in the systems engineering and modeling space, with the focus shifting to network design and early software development. Deepak has published over 50 articles and presented at over 30 conferences in EDA, semiconductors, and embedded computing. Okay, let's get started. Over to you, Deepak.
Thank you, Dan, for that fantastic introduction. And good morning to one and all. Thank you for attending this webinar by Mergeless Design, co-sponsored by SemiWiki. Today, our discussion is all about architecture exploration of building systems on chip using the VisualSim RiskFi and ARM-based hybrid processing systems. I'm your host, Deepak Shankar, and I'll be walking you through the problems, the challenges, the methodology, the solution, and the benefits that go about doing architecture exploration around the RiskFi processor. Just a quick introduction to Mergeless Design. We've been around since 2007. We started off primarily with building large network systems and then gravitated to semiconductors and also to IP. We've got development and support centers across the world, so anywhere you are, we're within a few hundred miles of you. We are the largest provider of intellectual property and software for the system architecture exploration market. Over 200 products in semiconductors, processors, networking, multimedia, automotive, defense, and space have been developed by doing architecture analysis and trade-off using our VisualSim modeling and simulation product. A quick introduction to the product itself, VisualSim Architect. It's, as mentioned, is a modeling and simulation software, allows you to explore the performance, power, functionality, tuning of your application, and a variety of other related operations such as reliability, fault tolerance, efficiency, quality of service. It's completely a graphical and hierarchical environment, so it becomes easy for debugging, but also for demonstration and training purposes. Now, VisualSim Architect starts off at the IP level, so it can be an accelerator, can be a network, message network, can be an AI component, to the full SoC that may contain a combination of processors, DSPs, GPUs, AI accelerators, memories, display controllers, buses, NoCs, things like that, all the way to a full system. So it can be like a backplane with OpenVPX or PCIe, or it can be a network system with multiple high-performance computing like in a data center. And finally, the software, which can be a combination of device drivers handling a large number of interfaces to an application that is running intent, say a DSP function or a control function. One of the key aspects of VisualSim Architect is the ability to be able to connect with existing technology, be it semiconductor interfaces such as FPGA boards, emulators, can be instrument panels through a TCP or a UDP connection, to simulators on existing computers, and finally, entering your C, C++, Python, Java, any combination of code. So it's really a comprehensive architecture modeling and exploration solution. Now, what is the scope of system architecture exploration? So before I go into the details of, trying to explain why architecture exploration done this way is far more efficient, is really to understand the scope. System architecture exploration really starts at the very early stage of your design process. So it's really about you receiving requirements from customers, or you have new ideas, or marketing has come up with some proposals, and they typically are in a requirements document, can be in DOORS, can be in SysML. And the goal is to take all of that and convert it into a combination of traffic, workloads, use cases, and construct a block diagram that you think is the initial starting point for what your system needs to look like. Then what you do is you run a variety of simulations, run trade studies, workload analysis, traffic modeling, things like that to come up with a variety of specifications. So it can be at the IP core, within a core, it can be software performance tuning, can be system specifications for the entire design, which can be, like IoTs talking to a data center, or it can be a full SoC. So it can be a combination of any of these. But the whole goal is once you're done with VisualSim, you're never really done with architecture expression. Once you're completed the initial phase, you have a fully validated specification that you can go for integration or development. This is a key aspect. You really want to eliminate all of the bottlenecks, eliminate all surprises before you go past. Now, the one key aspect of software performance tuning that I would like to bring out, because it's kind of a new concept, is really taking your unique AI or software code and being able to run it on top of a fully validated hardware platform model, and then be able to execute it on that platform model and generate reports, modify the code, and then optimize it on the platform. Why is this unique? Today, most models that you get available will only tell you if your code has been executed. It does not tell you what is the quality of service, how much time did it take to execute, how much was the power consumed as a result of execution. This is the first solution that focuses on software performance tuning. And this forms a major aspect of what you can extend your architecture exploration model. So it goes beyond, once you've written the specification, it doesn't end there. There are a lot of other attributes. Software performance tuning is one of them. Now, there's always been a concern that architecture models tend not to be accurate. The reason is, you don't have a lot of information. You don't have the implementation details, like how the wiring goes, how the layout goes, things like that. But in reality, you can get extremely accurate system models that can provide you more than enough data to determine exactly what is going to happen in your real system. So this one here, for example, is a micro benchmark of a model we ran in VisualSim, which is for these three benchmarks. And as you can see, between the FPGA and the VisualSim, there's less than about 8% difference. Matter of fact, we're running this on an ultra-scale board. So it's not only validating an A53-based SoC, but it's also validating against an FPGA model. So, a real FPGA. So you can actually see how you can validate these different types of designs, but also see the level of accuracy that you can receive. One of the questions that always comes up is, hey, I know performance, yep, I can understand that, but how do you validate power? And as you can see here, our power is actually far more accurate than even the performance model. Why is the case? Because we have an integrated solution. We don't distinguish between performance and power during the architecture exploration phase. So power is really understanding what your workload is, what your use case, the software application, what is the hardware platform, what are devices turned on, and also the complexity associated with definition of different power levels for different states. So it can be active, standby, idle, wait, deep sleep, whole variety of things. And they can be also, like for this task, is this power, for this task, is different power. So it's really more of an equation-based power description. So that's one of the reasons why you can see this level of accuracy for a power model. Now that we understood a little bit about the scope of system architecture and also the accuracy, let's focus a little bit on what are the challenges in designing a new SoC. One of the biggest challenges is that when you're designing a new SoC, is the total uncertainty. What is going to be my end application? All right. What is going to be the use cases? How many users are going to be accessing it at the same time? What is going to be the workload? Really, without being able to understand that, it's really hard to say, this is what my topology looks like. So you end up doing a lot of assumptions. You create a huge amount of flexibility. creates a product that might be expensive, over-designed, and potentially have problems with too many flow controls and buffers that may cause a bottleneck by itself. The other aspect is because you're not aware of what the real system is, you end up creating these random test benches as opposed to more appropriate test benches. So you really need a reference model that would run the code and tell you these are the configurations for which you would run it. Now, the other aspect is the impact of software workloads and task partition. So today, you might have a model that you might get from your vendor that says, hey, here's a model, you can run your software on top of it. Unfortunately, they don't give you a model which is like 8 cores or 16 cores or 32 cores. So how do you partition your workload? How do you allocate to different clusters? Or how do you say this cluster needs 4, this cluster needs 8, or this cluster needs slower processors, this cluster needs faster processors, or maybe like big and little within the same cluster. And then associated with that is really sizing it. How fast should my core run? Because if I run it too fast, power goes up. If I run it too slow, applications start getting stalled. So there's got to be some sort of a trade-off between performance and power. And lastly, a lot of optimization is going now, especially with with the introduction of AI and displays and things like that, where if I add these vector functions into my RiskFi ISA, I could essentially eliminate the GPU because the GPU part is very small. Or maybe my custom AI functions can be integrated ISA, so I don't need accelerators. It can be done through the same pipeline. But what does that change? Do I need dedicated floating point execution units for those? Will that increase the cost? Will that make it a bigger chip? How do I analyze all of these? These are all the basic challenges that you find in designing a new SoC. Now, great. So now you understand the problem of designing an SoC. Now let's look at the challenges in the architecture exploration as a solution. So everybody knows architecture exploration. Everybody knows that you can get phenomenal results with architecture exploration. You can do performance studies, you can do power studies, you can do functional, you can do quality of service, fault tolerance, whole suite of these things. But what are the challenges? I think the biggest challenge is finding IP blocks, finding blocks that are ready to go and use in creating an architecture model. So for example, if I call up vendor A and say, hey, give me a RiskFi model of your multi-core, or you call up, say an interface provider and say, hey, give me an architecture model so I can run a simulation, they aren't available. So you really need these models. A lot of people tend to focus on fast or virtual prototyping models. These are great for early software development, but they're not great for doing architectures, making decisions. So that is where the architecture exploration kind of stalls, because people try to use virtual prototyping environments and say, hey, can I do architecture exploration there? No, because it doesn't have accurate timing. It doesn't have the pipeline. It doesn't have, for example, in your cache, you're not going to get things like, for example, inclusion, exclusion, or for example, get you a pseudo-random replacement policy. Now, of course, there's a lot of open source discrete event simulators, System C being one of them. But the problem is, going back to point number one, you still need to build the models. Very expensive. You need to really understand the concept abstraction and modeling to be able to put, accurate models, but at the same time, fast models. And of course, the last year, you collect all the data. But how do I analyze the data? How do I compare? How do I visualize the data? Again, you got to use Python programming to get in the format, maybe use third-party tools like GNU plot and view the results. So now you've got another source that you have to work towards. So really, it's kind of a challenge, which is, like availability of models and the amount of resources that are required. This is one of the reasons that's holding back architecture exploration as a solution. So, Mergeless Design introduced the concept of hybrid processing. Why is it called hybrid processing? The main thing is you're getting cycle level accuracy, but at the speed of stochastic models. And you get a vast library of components, both generators, and also vendor specific. And you have the ability to run software code traces on top of this hardware model. This is a major aspect. You're getting performance to be able to run software trace models on top of this, software trace on top of this model, which is a major deviation or a major diversion from what used to happen in the past. And of course, the hybrid processing concept also comes in with all the reports and statistics and flexible viewing mechanisms. The reason that is important is because you don't have to go to a third-party tool. You don't need Python programming. You just run the simulation, you view the results in real time, or you run the simulation, view a bunch of simulation results, combine them and view it in one view. So this is another important aspect. The other thing is everybody in the company can use the same platform. Whether you're building the IP, say you're doing the processor pipeline, or you're building the entire SoC, or you're building an application demo so you can share it with the customer. All of these folks are now using the same VisualSim hybrid processing platform. You don't need a separate environment. It's all self-contained. Now, what does this hybrid processing environment consist of? As you can see, it's a very large package. It gives you everything that you want to build up your SoCs, but at the same time, it also connects to networking interfaces to create a full board, also connects to requirements tools, also connects to like your performance and power related information. So it's really about getting everything together within one single platform. So the key thing about it is that you now have the ISAs for all the major technologies. You have off-the-shelf components like an A65, an AE, or an A53, or an A77, or A68AE, or an N1 from ARM, or a U74NC from SiFive, or an Arteris FlexNoC. So you have these about 50 to 60 different vendor technologies that are also shipping as part of a hybrid processor. Now, is this sufficient? Yes, it is. But one additional thing is you now have the ability to integrate your software. Remember, in the past, if you needed an architecture model and they gave you a good, accurate model, it can take you days to simulate with the software. With this, no, you no longer have to do that. In about 30 minutes, you can simulate something that might take in a real platform, maybe 1 to 10 milliseconds. So you're now running at a level of accuracy, which gives you 2 to 5% off the real number, but at simulation speeds that are like between 50 and 100,000 instructions for the entire SoC, not one core, not one cache, the entire SoC, a major shift. So software, we have a technology that allows you to take your software code and create it, you compile it with your standard ARM or RiskFi or x86 or Spark compiler, and then you import it into the model, and you can now run it across a multi-core. So multiple cores can run asynchronously different software tasks across their particular system. Now, what are the applications? I mentioned the hybrid processing can actually integrate every aspect of the company. At the IP level, you can do a comparison. Like I'm using ARM or I'm using RiskFi from the same vendor. How can I uniquely differentiate mine versus the competition? So, I have to understand what's going on inside. What is my MOP cache, or what is my branch prediction, or, how does my dispatch criteria change? If I change one of those, what happens in my system? Similarly, at the SoC, am I really getting a benefit if I upgrade from, say, ARM 8.2 to jumping directly to 9? Or, for example, I might look at, going from, say, an A53 to A78. Am I getting a jump, boost on something? Or, for example, I'm adding new instructions so that I can combine my CPU, GPU, and my AI into a single core. How does that impact my system? And then at the system level, you're looking at a target application. So I'm developing a router or a multimedia entertainment system or a surveillance system or say a radar or a communication system or a LiDAR. How does this target application work with the SoC that I have developed? What is in it for the customer to buy this product? To really be able to understand that, I can simulate the whole system now. Even before I had the SoC, even before I had the software, I can demonstrate to my end customer a major jump from what you're doing today. And last but not least, I have device drivers. Lots of them, they've got 40 or 50 different interfaces. Device drivers can have greater overhead than even your hardware delay. So which means that now I'm going to start losing data. How do I prevent that? Start moving them to multi-controllers or start moving them to multi-cores. What is the strategy I've got to evolve? So you can really start looking at how software is now getting integrated into the architecture exploration. Without the software design being integrated, the architecture exploration is only limited view, doesn't have a global view. Now, let's take an example. Now, this is at the IP level. So what you're seeing over here is I've got two SiFive U74NC cores, and it's got two levels of caches within it. So within each cluster, there's a shared L2. We've got 4 cores within each of the clusters. And then you've got an AXI bus and memory controller. Now, in a normal system, you like load it up, run the software, see what happens. Here, we do something more intelligent, which is really your concurrent execution. What does that mean? I can have multiple applications. So for example, at the same time, I can have multiple IOs, which is represented by the yellow blocks, which we call traffic or an interface, feeds into the system that loads up this, the memory and then triggers these, the processor to start running. Now, each one can be triggered to run on a different core. Now, you can separate the clusters or you can like share the clusters. We're doing coherent systems, any combination of those. So what ends up happening is you now have the ability to evaluate how your cluster with those 4 cores really is going to operate based on your particular configuration. So if I change any of those parameters in blue that you see on the top right, how does that impact my systems? So this is at the code level. Now I can take these cores, add GPUs, add AI, add tensor processors, take all of those, and then put the whole system together and even have a system level cache between them. How does this overall SoC behave? Now I got a different set of parameters that I'm starting to work with. Now if you notice here, earlier on it was more of symmetrical heterogeneous cores, but now I've got fast clusters, slow clusters. So I can now start putting more complex designs together, but now in the context of a full SoC. So what are the types of analysis? As you can see on the top left, there's a matrix multiply, which means that I'm looking at what is the quality of my tensor processing. On the top right, I can see the latencies across my fast cluster. Lower one is on the slow cluster. But here's the important thing. Relative to all of this, I can see right in the middle at the bottom, the red lines being what is the average power, and the blue line telling me what the spikes are. By spikes, what I mean is every time a new device comes on, the power keeps adding up at that point. Every time a device shuts down or goes to standby, the power keeps reducing. So cycle by cycle, I know exactly what is the maximum power that's required, and also what is the change, what is the transition happening. So I can get a good feel for how much power this system is going to take, and also what are the spikes, what are the peaks. So that helps the thermal guys and the mechanical guys make decisions. The last one here is looking at my array. So these are the walks at the bottom left, and it's showing me what the latency is for each of the walks. Now this one here, earlier on we were looking at RiskFi. This one here is now looking at an A65AE for which there's no vendor available architecture model. You're looking at some CMM600, again, not available from any vendor. And you can see that the whole system has been assembled. You can see that we've got clusters with DSUs. Within the clusters, we got multi-level caches. and then you got memory controllers, and at the bottom, you got what your use cases are. So it kind of combines all of these within one particular design. So looking at the entire SoC now. Now, what are the kinds of plots? So here you can see the top left is a behavior latency plot, which is how much time is it taking for the entire behavior from end to end, from the time it hits the IO to the time it completes. What has really happened? It shows me what my latencies are. The bottom left shows me the latencies on each of the cores, each of the individual cores. What is happening? What is the latency every time tasks are executed just within the core? So it's core latency, doesn't include the complete task application, which is a sequence of tasks. That each task is measured as a latency within the core. Top right shows me my power consumption. So you can see most of it is below 1 watt of power, but then I got these spikes that hit 1.2 watts of power. So that is something to consider as as something where, hey, why do I have all these spikes? Can I offset some of the code? So that way I prevent for these spikes to go up, which is almost 20%. I can bring it down to 1.0, which means my cooling is at 1.0, not at 1.2. That's a substantial saving on the cost of your SoC. And of course, you can see what is the effective mix on these things. So you can see most times I do get my peak of 1.2 megahertz, but it's a very, very short period of time. So you can see most of it is about 800 megahertz or maybe 750 megahertz is the average, but I can still see the spikes during which I have to, hit it up to the highest level. It gives me that as well. The last one is I can go down into an IP, into a particular IP. So in this case, we're looking at the internals of a particular pipeline of a processor core. And you can see how all these different stages have different requirements in terms of the analysis, in terms of parameters. And we have modeling components that represent each one of these as part of the hybrid processing library. So what happens? You now can assemble the core as not just one component, but as a system of components. So you can actually see what is happening in each stage within the pipeline. And that way fine tune the architecture so you get extra performance. Now, in conclusion, architecture exploration, because libraries, VisualSim provides intellectual property and software to help you get ramped up, it's really easy, fast, and accurate. Now, because we're integrating at the IP level, SoC and systems, the entire company can work together. They can all collaborate and build a really kick-ass product. And finally, the accuracy. If you saw right up front, I was able to show you the accuracy is so high. You're between 92 and 98% accurate, which means that now you're at the level of accuracy as your silicon, but maybe 2 years prior to the silicon being available. And of course, you're running simulation speeds that enable very large scale testing. So we have customers that are running 25 to 30 milliseconds of real life within less than a day in a cycle level accurate model. With this, I would like to wrap up this presentation. I appreciate everybody attending and involved. Over to you, Dan.
Great presentation. Thank you, Deepak. Let's start the Q&A. First question. Many companies are designing RiskFi products today. What are some of the architectural challenges they have encountered?
This is an excellent start off, Dan. One of the things we're finding is that RiskFi is being used all over the place: medical, industrial space, automotive. So they're experimenting with in every space. And what we're finding is in every space, the architecture requirement is fairly different. For example, functional safety and power consumption is a major consideration in the automotive. Reliability and like fault tolerance in the space area. And then we have a more traditional business where we're looking at things like what's the expected performance? Where are going to be my bottlenecks? What are going to be the resources? What happens if I have, like a system level cache that connects to 32 clusters? So all the traditional questions are being asked also in the RiskFi space. But now there's another problem that's coming. The problem is that most of the companies have been using RiskFi as more like at a microcontroller level, but now the requirement for RiskFi is starting to go up to a high-end mobile or even to like a desktop. And in those cases, there's like two things. One is how fast is it and how much power saving is it relative to the incumbents? And you know who the incumbents are. And the second question is, what should be the topology? I mean, do I put a network on chip and then, connect up a system level cache? Do I start doing cache caching so that I can reduce the load on my network within the chip? What if I use AXI buses to connect it to memory? What's going to be the performance difference? So, and then comes the questions within the core itself. What happens if I add a little more vector functions? Can I get rid of the GPU? Or, for example, if I have more number of integer units or floating point units, how does that change the whole landscape? Does RiskFi become much better than the incumbents? So these are a lot of questions that people are always asking me. I mean, almost on a daily basis, I get these questions.
Great. Another question, can the RiskFi system models developed by the architecture teams be reused, and if so, where?
Oh, this is a good follow-up. See, RiskFi and actually all performance models tend to be in the architecture domain, and beyond that never goes out. But the companies that are really taking benefit from it, and RiskFi especially is very important, is that they can be used for early design wins. They can be used for debugging. They can be used for demonstrations. They can be even used for like publishing papers to show people why RiskFi is critical, why RiskFi is going to be a trendsetter and is going to make a big difference. So I would say that you're really going to see RiskFi, these system models of RiskFi being used across the board, right from your concept to the end of life of the product.
Okay, but can people really conduct system level power analysis on RiskFi SoCs?
They have to do it. They don't really have a choice. If you really think about it, I'm designing this completely new thing. I've never done a RiskFi before. I don't really have a chip for reference. So what am I going to do? If I just do an Excel spreadsheet and I've got 30 different active states, or I have a specialized power management algorithm, or like based on the function that's executing, the power is going to be different. There are going to be so many concurrent operations. There are going to be so many things that without simulation, without knowing what my workload is, without knowing what my use case is, impossible to get a feel for power. And I believe that only system level power can actually do that. I mean, if you're trying to do it at the RTL level, yes, you're going to know what your layout information is, but you're not going to be able to run a complete spec mark. You're not going to be able to run a space benchmark or a, say, like an AutoSAR application. So only at the system level you can do it, and that's where you should be running those the power analysis.
Another question about architecture models. Architecture models are considered inaccurate and the output from the model is not necessarily taken seriously. How has hybrid processing from Mergeless design addressed this issue?
One of the biggest problems with architecture models is that there is no reference, which means these end up being untested models. They're like, hey, here's a stochastic model, here you go, start working on it. What hybrid processing has done has really transformed the whole architecture and system modeling industry. If you think about it, back in 2000s, we had Denali software that brought out these IPs and software for verification. We're going along the same path of saying, hey, we're really providing a fully validated set of library blocks, whether you're getting it from vendor A or vendor B, or whether you're you need some power illustrations or you want to customize your cache. There's library blocks for those that have already been fully validated and provided to you. So that is the first reason why you're going to get these architecture models to be very accurate. The second thing is a large number of companies are already starting to use it. Our previous generation product has over 250 products that have been built using it. Hybrid processing, we just started it. I mean, it's been 18 months of work, but we just launched it. And now we have almost like half a dozen companies already, like at advanced stage of development using these hybrid processing, and they're starting to identify, like performance issues, bottlenecks, things like that. So I believe we have moved away from where people are thinking its architecture models are incorrect to like seriously using them, saying that, this is the best way to go.
Got it. Okay, another question. Traditional approaches to system design were expensive and in most cases abandoned after a few projects. Why was this the case, and has this changed?
Sure. In the past, if you looked at about 10 years ago or even 6, 7 years ago, there were only really two ways you can do system modeling. You could write a lot of system C code, or you could use an Excel spreadsheet. The first one, when you write system C code, it's written by one person. He runs a simulation. He goes off to another job. Now this needs to be handed over to somebody else. That somebody else has no idea what the earlier guy did. It's not documented. So it becomes very expensive that, you go project to project, and, after you finish one project, either you have to completely scrap it and rebuild it because it was really customized for that approach, not really made to plan for the future. So as a result of that, it started becoming very expensive. And then, it just starts getting fatigue when, I have to make changes every time, not just change a parameter and run it, but rather have to rewrite the code. It ends up taking so much time that you've already, like gone past your systems engineering deadline. What has changed with hybrid processing and what has changed with what we're doing with VisualSim, and you saw this in the presentation right now, is the fact that now we have these standard library blocks. So irrespective of whether you're doing ARM-based or RiskFi based or a cache or a DDR4, there's a standard library component. So if use it on project 1, it's going to be the same block on project 3, 4, 5, 6. Even if you're using a new component, it's based on these half a dozen existing components that you're building up these new ones. So anyone new coming along can immediately read it and understand exactly what's going on. So reusability is really the cause of reducing the cost and also not being abandoned after a few projects. They continue to use it.
Got it. So let's talk about hybrid processing. It's a new concept to architectural exploration and system level analysis. What's the backstory here? Why is it called hybrid processing?
Yeah, so a lot of people have been asking me this question about why is it called hybrid processing. See, two trends have happened. One is IP vendors and EDA vendors have stopped providing architecture models for high-end products, be it processors, interfaces, interconnects, memories, and things like that. And we said, okay, we have to come out with something that really helps our customers. There were two major problems. One is either they were inaccurate or they were too slow. Hybrid processing was bridging those two gaps. So we had cycle level accuracy, but at stochastic model speeds. So that was one thing. The second one was reusability. It was hybrid because you can use it to model the IPs, the SoCs, the systems, and even a full distributed network. So that was another reason for the hybrid. And the third one is all of these were template based. So earlier ones were always fixed, they were always static, or they were fully dynamic like an Excel spreadsheet. So we said, okay, we're going to merge it and make it hybrid where it's template based. So you change the values in the template, it starts behaving like a new component. So what has really changed here is the fact that you're running about 50,000 instructions, 50,000 instructions for full SoC per second. And you're at 98% accuracy for performance and power. This is what hybrid processing has brought to you.
Great explanation. This is a good stopping point. Thank you for your time, Deepak. It was an excellent presentation. And thank you everyone for participating in the SemiWiki webinar series, and have a good day.
Thanks a lot, Dan, for your time, and thanks a lot to everybody for attending this session.